The pulsating star M82 X2 is an example of bodies that emit more radiation than is possible within the current laws of physics, and a new study suggests that magnetism is the cause of this phenomenon. Scientists have confirmed the existence of a pulsating star located 12 million light-years away, as its brightness exceeds the limits set by the current laws of physics. A new research paper provides evidence that the magnetic field of the star is so strong that it transforms atoms into long lines, allowing them to reach levels of radiation that were previously considered impossible. In 1924, the astronomer Arthur Eddington proposed a limit on how bright a star could be based on its mass, without collapsing or tearing itself apart. Although Eddington's limit has been modified to some extent, it still holds up to this day against the test of time. The discovery of the star M82 X2, along with multiple extremely bright X-ray sources, challenges Eddington's limit. These objects appear to emit hundreds of times more electromagnetic radiation than their mass allows. Nevertheless, the research paper validates this problem and offers a preliminary explanation for it. The star M82 X2 was named after the galaxy M82 where it is located. Although it was known to be a source of X-rays, scientists only noticed the intensity of the brightness of the pulsations of the star M82 X2 in the X-ray spectrum during the explosion of the supernova SN 2014J in the same galaxy. Pulsars, like all neutron stars, have a narrow range of masses, and Eddington's limit sets the maximum amount of energy a body can release. However, the star M82 X2 pulsates with a brightness that is sometimes 100 to 500 times stronger, and then returns to its original brightness. Initially, it was believed that M82 X2 was a black hole because its large mass supported such brightness, but this idea was largely dismissed. An alternative explanation suggests that the observed brightness is due to an observational error caused by the concentration of light in a beam directed towards us instead of spreading in all directions. The lead author of the study, Matteo Baschetti, and his co-authors examined data from 7 years of the Nuclear Spectroscopic Telescope Array, NuSTAR, and measured the orbital decay of the star M82 X2 and its companion. This provided strong evidence that the star shines in all directions. Researchers claim that magnetic fields with intensities billions of times stronger than Earth's magnetic field exceed this limit. We cannot test the outcomes of these fields. Some pessimists suggest that some physicists tend to blame magnets or interference when they cannot explain a phenomenon, similar to what scientists in the Middle Ages did when they attributed phenomena to miracles. Who truly knows the mechanism behind magnets? According to a statement by Dr. Baschetti, he said, "These observations allow us to see the effects of these extremely strong magnetic fields that we cannot produce on Earth using our current techniques." Eddington's limit was found because photons exert a force on objects, as seen in the Crookes radiometer experiment. Based on most other sources of light, this force is small, but in the case of sufficient brightness, it can overcome the internal force of gravity responsible for the cohesion of objects. The source of ultra-bright X-ray emissions, known as ultraluminous X-ray sources, ULXs, is believed to be attributed to the accretion and fall of matter onto their surfaces. NASA conducted calculations suggesting that the fall of a marshmallow piece onto the surface of a neutron star could release energy equivalent to 1,000 hydrogen bombs. However, if the X-rays exert a force greater than the gravitational pull of the object, then the gas or marshmallow would not be able to reach the surface. The authors demonstrated that the star M82 X2 steals mass exceeding the mass of the Earth from a larger but less dense nearby star, providing it with enough energy to emit the observed brightness in all directions. The problem lies in how the gas can escape the force of the incoming X-rays in advance. The authors speculate that the magnetism is strong enough to stretch atoms into thin, long threads that surpass X-ray photons. Although this idea has been proposed before, testing it remains impossible.